The first garbage collection mechanism that we actually want to talk about is reference counting. Now, reference counting has been implemented in a whole bunch of languages, including, up and coming languages like Python and others. And the idea behind reference counting is the following. Every memory segment or whatever, however, every box that we showed in the picture before, right? Actually, besides having the data that it holds and the pointer to the next box, also holds a counter. The counter says how many pointers are pointing at it. And the idea is that as pointers go down to 0, we leave the memory intact because you might have a bunch of pointers pointing to the same actual memory location. But the minute the pointer hits 0, all that means is that nobody's pointing at it anymore. By not pointing at it anymore, you're actually saying, I am garbage. And by doing that, the system will go and reclaim that box into the free list that we saw before. So we get our little free list, and we took off chunks of it, and we put them into all kinds of variables, and we were able to have a whole bunch of different pointers pointing at the same memory location, and that memory location said, "Oh, X number of people are pointing at me." And every time you had to reassign a pointer somewhere else, so the number went down, and the other guy's number went up. Anytime anybody went out of scope, the counters went down. And in that way, we were actually keeping tally of how many more pointers are pointing at a specific memory location. And as long as somebody's pointing at it, it's not garbage by definition, because that just means it can be accessed by somebody. The minute the number of the counter goes down to 0, well, that just means that nobody can access that memory anymore. It is garbage. Let's recollect it. That is reference counting. That's how it works. And it's very similar, by the way, to smart pointers in C++ that we spoke about. Same idea behind what's called shared PTR, right? The smart shared PTR pointer, same idea. And it's done here, obviously, behind the scenes, and you don't have to deal with it. So you just go out of scope, you don't care about the variable, and then you let the runtime behind the scenes deal with actual garbage collection. This system has a whole bunch of problems. It's very efficient as far as there is no dead time, meaning to say, if you think about it for a second, it's constantly collecting garbage. It doesn't get to the point where, oh, I need more memory, I don't have, let's start some kind of algorithm, figure out who's garbage and who's not. It's forever collecting the memory, and any memory that became garbage is immediately reclaimed, and any memory that's not garbage is still there. And therefore, if you try to allocate memory and there is none, all that means is that there actually is none. It doesn't mean that there's garbage out there and you just have to collect it and then you might have. So it's actually spreading the cost of the collection over time. That's a big advantage of this system. The downsides of the system is 2 or 3-fold. First of all, the question is, what is the ratio of data to counter? We were talking about a box of memory that looked like this. We had our data segment, and we had our pointer segment to the next guy, and now we have our counter segment. And notice that we have over here overhead. The counter and pointer segments, in a sense, are overhead. The counter segment is the overhead for this type of garbage collection, and the pointer is overhead for actually just managing memory. Now the question is, what is the ratio of the counter segment to the data segment? If the ratio is very high, right? If the ratio is very high, so then the cost of this system is very high, which means if we have very little boxes of memory, which means the data is actually small, and the counter is also constant size, it's just a counter, so then the overhead is actually very high. But if we have big boxes in memory, so then the data segment is very big, the counter remained constant, and therefore the cost actually went down. But having big boxes of memory just means less flexibility, because you can only allocate boxes of memory. You can't go and allocate a part of a box. So if I go and I make big boxes of memory, so I'm actually wasting memory. So there's an offset here between the ratio of cost to data and the offset is also a function of how flexible you are in allocating the memory. The second problem that we have with this thing is the same idea that we had with smart pointers. Suppose for a second that you have a piece of memory, a box of memory, that points to the next guy, that points to the next guy. We have our circle in memory. And from the runtime stack, we were pointing at this guy, right, from the runtime stack. So if we had to ask ourselves about what is our counter count, so here we have a 2, and here we have a 1 and a 1 and a 1. Now suppose for a second that the runtime stack guy went out of scope, so this counter went down to 1. None of these are garbage, so they won't be reclaimed by the system, okay? And therefore we are getting actually a hole in the system that's not being reclaimed. This is all garbage, our definition of garbage, because they can be reached from anywhere. I mean, the link from the runtime stack has disappeared. They can be reached from anywhere, but they are still just there, right? So we actually have garbage. So our reference counting system does not succeed all the time in actually reclaiming all our garbage. Now, this is a known problem. And as I said, Python, for example, does reference counting. So how do they overcome this system? The answer is, this problem, sorry. The answer is that once in a while, once in a longer while, they actually run a different garbage collection system. They run a mark and compact. They run mark and sweep. They run a different garbage collection system, which does not have this problem, which we'll see in a minute. So by running reference counting all the time, they're actually reclaiming garbage and allowing themselves the breathing room to keep going, keep going. But once in a while, just to make sure they're not losing memory to this, what's called memory hole, okay? So they actually run another type of garbage collection to fix this problem.